So we're doing a little homework check-in here, and let's go there. Number 10. All right, okay, so we did one like that in class a few days ago. Let's do another. So let me grab a screenshot of that. So the trick when you have a radical plus or minus something is to apply the conjugate to clean up the fraction. And let's see, that needs to go on a new page and be a wee bit bigger. There we go. So we want to find that limit, and if we try to apply the limit law saying let's take the limit of the top and the limit of the bottom and the limit inside the root, those work only on certain conditions. And so if we check the limit laws here, I could spell check today, and we plug in 0, let's see, we're going to get the square root of 9 minus 3 over 0, which is 0 over 0, which is indeterminate. So the indeterminacy here is actually nice because that means there's a possible solution. So then we take a look, and we could look at it graphically to guess at the number for sure, but let's see if we can do it algebraically. And the trick is to apply the conjugate of the numerator. So I'm going to take that square root of 6x plus 9 minus 3 and multiply it by the conjugate, which is the square root of 6x plus 9 plus 3. And to keep the fraction equivalent, we need to do the same thing in the denominator. So we need to multiply that 5x by that same sum. And let's see, there's not really much point in multiplying the denominator, but we definitely need to multiply the numerator here. And so square root times the square root cancels, so that's just going to give me 6x plus 9. And then the minus 3 times plus 3 is going to give me a minus 9, so that's my new numerator. And the middle terms cancel out because this is the difference of squares. So the 9s cancel out too, leaving just the 6x. So we've got 9 minus 9 is 0, and then that allows us to take x divided by x is 1. So then this limit cleans up to be the limit as x goes to 0 of 6 divided by 5 times that sum, square root of 6x plus 9 plus 3. And now that we've eliminated the 0 in the numerator, we should be okay. So if we evaluate again here, we're going to get 6 over 5 times, if we plug in 0 for 6, we get the square root of 9 plus 3, which is 3 plus 3, or 6. 6's divide out, and it looks like it should be 1/5. And we could check that by graphing this sucker. And so that's worth, actually, I'll leave that up to you to graph that. So again, if this were a test question, I only get one shot at it. So I would definitely whip out GeoGebra or Desmos and graph this to see that when x is 0, that y seems to be about 1/5. Okay, next question. Let's see, 2.4, number 10. Let's jump assignments. Shrink that. We're almost done with chapter 2. Are we allowed to use GeoGebra or Desmos on tests and midterms? Cole asks. The answer is yes. So, and I'll talk more about that later. The tests are going to be take home in 2 parts. One part will be timed, and the other part will be kind of, you get a couple of days to get it done. And you're on your own. I have no control over what you do and don't do. I will make suggestions about what I'd like you to do. But if I make too many suggestions, I find that's a tax on honest people. And so I try not to make too many. And so I'll talk about what I think is legitimate and what I think isn't during a test. And basically it comes down to, as long as you do it on your own and don't consult another human, I'm okay with it. And there are wild apps out there that do math for you, and I'm going to go over some of those as we move along in the course. All right, so number 10 in section 2.4, so you have this beautiful piecewise function, and both Desmos and GeoGebra can do piecewise functions. I don't know if anybody noticed in the description of those videos I posted for yesterday's class, I put links for Desmos and GeoGebra on how to type something like this in. But the key here is we don't have a B. And so I just want to play around with this graphically for a second. To be continuous, these two pieces have to meet. So let me write this down on paper so I can switch to another screen. 4x minus 6 when x is less than or equal to 3. And then 7, negative 7x plus who knows what otherwise. Okay. So actually, let's look at it on paper first. Screenshots. New page, please. Make it big. So, you know, I can graph this pretty easily by using slope and intercept, but I'm just going to make a table of numbers for a second just to play around with what's going on here. Come on, pen. There you go. So x versus y here, if I happen to pick numbers that are less than or equal to 3, so for example, like 0, 1, 2, and 3, then y is equal to 4x minus 6. However, if I happen to pick x values that are greater than 3, like 4, 5, or 6, then I have to let y equal negative 7x plus b, right? So just quick here, I know the y-intercept is negative 6 and the slope is 4 over 1, so every 1 it rises 4, so that would be negative 2 and 2 and 6 there. So I don't know what b is yet, so I can't calculate these points, but let's just consider a graph. Let's squeeze it in here. And assume each of these is worth 1. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This one for x less than 3. And let's make a little reminder line here. 1, 2, 3 is right here. So, oops, that's not what I want to do. Choose yellow. At this yellow line, we switch, you know, the definition of which way we calculate. So that's a boundary line right there at x equals 3. So let's see, I lost track. Where is negative 6? 1, 2, 3, 4, 5, 6. Okay, so, oops. Come on, pen, please do my bidding. There we go. So there's my negative 6 right there, and then the slope goes up 4. So 1, 2, 3, 4 over 1, right? Up 1, 2, 3, 4 over 1. Let me do that one more time. 1, 2, 3, 4 over 1. And that point is definitely part of this function here because it's less than or equal to up there. So I get that there. And then this function right here, if you think about it graphically, if I want this thing to be continuous, that other function has to start there. So let's say I'm going to use red for this part right here. That function has to start here and have a slope of negative 7. So I know what it's going to look like. From that point, it's going to have to drop 7. So that's going to put me right there. And so that's what this one's going to have to look like. All I need to know is what is its y-intercept. And bottom line is, I know it has to pass through that point right there. That is the point. Oops. And that is the point 3, 6. So as long as this function right here passes through, this part of the function passes through 3, 6, it's going to be continuous because they meet right there. Okay. So I can just plug in those numbers here to make that happen. So I'm just going to replace the y with a 6 and the x with a 3. and out pops B once I do that. So what's that, 21 negative, add that to the other side. So B has to be 6 plus 21 or 27, which given the steepness of this, that, it's got to be way up there. So that does seem reasonable. And we can double check that that is indeed 27 by plugging in some numbers to check. So for example, I'm at 3, 6 here. I know if I go up 7 and left 1, that's going to put me at what, 13 up there. So 1, 2, 3, 4, oops. 1, 2, 3, 4, 5, 6, 7. So the next point, if it existed, but it doesn't, because I can only use x values greater than or equal to 3, would be up here. Why I'm even calculating that, I have no idea. Scratch that. We want x to be greater than 3, so we're going this way. Anyway, so this is a graph of the function right here. It's this V-shaped thing, and x has to be 27. To continue, if we plug in, say, 4 to that, we get 28, negative 28 plus 27, so we would get y as negative 1, and that is definitely the point I have graphed right there that I used the slope for. So again, we had to find the y value for 3 here, because these guys have to meet, even though this guy can't actually use 3, it has to be able to go right up to the edge of it. So we have to know what it is at 3 anyway. Okay, hope that was helpful. Questions further?